So I'm going to talk about the Liquid Metal project. This is a project at from a team of us who we have up here. We're at the T.J. Watson Research Center in Yorktown Heights, New York. This is the main IBM research lab. So I'll start by telling you something which you already know, which is in the last decade or in the last 8 or 9 years ago, frequency scaling pretty much came to a stop. Clock speeds on computer chips are not getting faster very much anymore. And so the only way to improve performance with chips going forward to exploit the more transistors is to exploit parallelism. And so we entered the multi-core era, which we're all familiar with. So let me just start by asking a question. How many people here have explicitly programmed for multi-core with threads or any other parallel? So almost everybody in the room has programmed for multi-core. And I assume by a multi-core you mean something like Intel x86 bunch of cores, small-scale multi-cores. One thing which you might be aware of is in the last few years become very hot is that there are much more high-degree multi-cores called graphics chips, GPUs. And over the last, especially in the last 3 or 4 years, these have become very popular. Here, instead of having a few, 2 or 4 or 8 cores, we have several hundred cores, perhaps thousands of hardware threads which can run concurrently. And people have realized that for lots of workloads, it's much more efficient and you can get much better speed and parallelism by programming with the GPU. And so we've seen the birth of GPU using GPUs for general purpose computing. How many people in the room have done GPU programming, programmed general purpose computation on GPU? All right, we have one. So GPUs are a fairly radical solution then perhaps for you, but if you want to get even more radical than a GPU in the world where we have very hard power constraints and difficulties with scaling, you can actually design your own hardware. So if you actually want to design your own ASIC, your own chip, you need a lot of money and a lot of time and a lot of expertise. FPGAs are field programmable gate arrays. This is hardware, basically programmable hardware, where you can create a hardware design and dynamically load it onto a chip. And effectively, it's a lower entry barrier to design your own hardware, and it doesn't run as fast, and it's not as dense as a custom ASIC, but it is a way to quickly prototype hardware. And once you can design your own hardware, you have your freedom. You can exploit extremely massive bit parallel structures. If you can do them, you can get rid of a lot of interpretive overhead. You don't have to worry about memory system hierarchies and things. If you can design the hardware to match your application, you can get much better performance. Has anyone in the room programmed it up using FPGAs? 3. So this is actually, I would have expected more doing GPUs and FPGAs, but not in this room. So this is the world we're going into. For those of you who haven't used GPUs or FPGAs, you may be wondering, do you really need to worry about this? Why do you need to worry about it? Let me start by a few motivating examples that we're seeing from a lot of our customers, and I believe you'll be seeing more and more over the first few years. So there are a few models of how we might want to use these specialized devices. Perhaps the easiest one to understand is using a GPU or an FPGA as an accelerator. So the idea here is that there's some part of your workload which for some reason, perhaps it's massively data parallel floating point computation, which a GPU can be done very efficiently, can do at higher performance, lower power per flop. Or perhaps there's some other kind of specialized processing which an FPGA can just do more efficiently than your CPU. And so a natural thing to do is just take part of your calculation which is running on your CPU, ship it over to use the device as an accelerator, run faster or run more power efficient, ship the results back and so forth. So effectively you're using this as an engine to offload some part of your calculation. This is extremely popular in the HPC world for things like oil companies doing seismic simulations, also in financial world. If you look at the top 500 supercomputer list, many of the highest performing HPC supercomputers now include GPUs at every node simply because they're the most powerful data parallel floating point engines that are available today. And we see lots of other applications which can exploit FPGAs as well. When we start talking about FPGAs, they have other advantages for which lend themselves to other kinds of deployment models. So one which is very popular is using FPGAs in what we call a network appliance platform. So FPGAs, you can plug your I/O, such as your Ethernet or serial bus or let's say your network, straight into the FPGA, and now you can design your hardware, so you can design your own network protocol to exploit very low-level structure. You don't have to worry about, say, running a custom operating system stack, and so forth. So you can get extremely low latency turnaround and very high throughput at the network bandwidth level, as long as you could basically, by moving your computation very close to your own custom network interface. And so there are a lot of, the FPGAs are used very much in telecom industries, financial industries, networking applications, effectively for low latency and high throughput network applications. So the idea here is that most of the computation will come in and off the network directly into the FPGA. Occasionally, perhaps some general purpose computation or control logic will execute on the main system, but the FPGA is the main locus of control of your calculation. Another model, which is sort of the same idea, is using what we call storage appliance. So in this case, the idea is if you can put an FPGA very close to your storage, and if you can architect your system to have much higher bandwidth between your storage devices, say your flash or a solid-state disk or even your regular disk, you can, by putting processing logic very close to that, you can get higher bandwidth. And so if you can do some of your query processing very close to the storage, you can reduce the bandwidth demands on your system bus, and you can basically offload a lot of your data processing in your big data world very close to storage. So this is what we call the storage appliance platform. This is very popular right now in big data database applications and so forth, and it just has advantages. IBM certainly has some offerings in this as well as other companies. So I hope I've convinced you that there are good reasons to use these architectures, and we're seeing more and more of these coming along. Yet most of you in the room had very little or no experience with this. One of the reasons why is because doing this kind of heterogeneous programming is not very accessible to mainstream software engineers today. One of the reasons is that each of these devices demands a different programming model right now. We're all very happy programming in high-level languages like Java or Python or whatever for our CPUs, and they provide a very high level of abstraction. If you want to program general-purpose GPUs, the current state of the art is to use something like CUDA or OpenCL. These are fairly low-level C APIs and subsets of C, which allow you to use the GPU, but you still have to program at a much lower level of abstraction. You have to learn a new programming model. You have to manually manage communication between devices. You have to be very careful about structuring your calculation to use the GPU effectively. So it's relatively painful, especially compared to our experiences in programming general-purpose processors. However, programming GPUs is like heaven compared to programming FPGAs. Those of you who have done this know, so first of all, programming FPGAs, most of the people who program FPGAs, they actually don't say they program. So you don't actually program hardware, you design it. You're a hardware designer, and you create a design, and you load the design onto the chip, and we don't even think of it, and that's why these are design languages, VHDL and Verilog. And these are very extremely low-level, basically circuit design languages that describe your computation. You don't have any benefits on the FPGA of an operating system or device drivers or memory managers or any of the things we expect, the system software which makes writing programs easy. So it's really a very low level, very painful experience compared to writing software to be able to use an FPGA in a heterogeneous system. So what we're trying to do is see how much we can do to fix this. So the goal of our project, it's called Liquid Metal, and we have a programming language called Lime. And our goal really is to try to make using heterogeneous systems with a mix of these kinds of devices accessible to a mainstream software engineer programmer, so that programming a heterogeneous system with a GPU or FPGA is not that much harder than as it is programming in a high-level language on a CPU today. And we think that if we're able to do this, we can make these platforms more accessible. And the platforms are coming. Right now, a very small elite of customers are using them. We expect that due to the trends in physics and the just benefits of using these architectures, there'll be more and more demand. We see this coming along, so we're going to try to make it more accessible and more like mainstream programming. So our strategy is we have a single language called Lime, which I'm going to describe in some detail, which looks very much like Java. We have a pretty rich tool chain to try to make programming in Lime resemble programming in Java as far as the richness of the tools, and we'll show you some of the details of how we go that. And also we try to provide especially runtime systems on which the system runs to hide many of the low-level details. So that'll be the content of the talk, is describing our approach to this. Before I go on, that slide I'll skip. Any questions before I get into the details of the programming model? All right, so let's talk about liquid metal. So our philosophy is that there is a single programming language, Lime, but we're not going to guarantee that we can compile all of Lime to every device. So there'll be different subsets of the language that can be compiled to each device depending on the constraints of the device. So what we have is the Lime compiler will spit out more than one version of different, it's a task-based program model of different tasks, depending on what sort of devices it can exploit for each piece of code. So all the code can be implemented to run on a JVM. We can spit out JVM bytecode and run on a CPU. So you can write a full program using any of the language constructs and it'll run on bytecode. If you want to run a particular task or a particular routine or a particular part of code on a device, such as a GPU or an FPGA, the compiler may or may not be able to generate code. And so the philosophy is that the compiler, you can write general code, and then the compiler has exclusions. The compiler will give a lot of feedback on reasons why it's not be able to compile a particular piece of code down to a device, and we try to make it as easy as possible then for you to refactor your code to satisfy the compiler, to tell the compiler more information that it needs to know in order to generate good code for a particular device. And I'll get into some details of what this looks like. So what is Lime? Lime, at a very high level, is very much like Java, but we add a couple of other constructs which allow us to compile down to these devices, which basically fall into two categories. One is isolation. So isolation is extra information to Java code which allows us to move computation around. And I'll show you some of the Lime constructs, the local keyword and immutable types, which enforce isolation on parts of the language which allow us to accelerate it. And then a lot of it's about abstract parallelism. So in order for the compiler to exploit highly parallel hardware and to move and schedule computation around, it needs to have a very good idea of the parallelism. So we're not taking a super compiler approach. We're not asking the compiler to infer parallelism from sequential code or anything like that. Instead, what we have are fairly high level constructs into the language that the programmer can use to tell the compiler, this is this style of parallelism. And once things type check, the compiler knows, okay, it's a way for the programmer to communicate parallel structures to the compiler, and then the compiler can map them down to the hardware. So I'll describe these in a little more detail. So our development experience, as I said, the idea is we're very big on an incremental migration, incremental refactoring. So the idea is you would prototype your code basically in Java. So you could start by just getting a functional version which works in Java. And to do this, we have an IDE, which is an Eclipse-based IDE, gives you all the benefits of the Java development environment, including editors and debugging and so forth. And then we want you to incrementally migrate the parts of your code you want to accelerate by adding these Lime language constructs, which express the parallelism the compiler needs to know. Any questions yet before I dive into the details?
One question, some of these isolation bound spaces, they look like the ones that were present in X10.
This is quite different from X10. Yeah, I can get to more details. I used to work on X10 as well. Let me present what we have, then I could describe. One thing at a very high level, we're not trying to solve distributed computing problem. We're not trying to express distributed memory cluster computing, which is the main focus of X10, so we're not trying to scale out to a cluster of workstations. Our constructs are really designed, the idea is you have a single node with devices attached and managing the details of particular devices. We're not solving the problem of how you would communicate across nodes. To do that, you would use message passing or X10 or some other model, but that's outside the scope of what we're trying to solve. Any other questions? Go ahead.
So you said you can incrementally move stuff, say, to the GPU or even to the FPGA. So do you need standard hardware for that? That you have a standard board where your system works, or is this flexible?
So it's different for different platforms. Basically, there'll be a set of platforms which we support, and we can handle those. So for the GPUs, we basically compile down to OpenCL, which is a standard for GPU hardware, which is supported more or less by NVIDIA and ATI and Intel and all the vendors. For FPGAs, there are really only two vendors that dominate the market, which are Xilinx and Altera, and we have support for both their tool chains. So as far as GPUs and FPGAs are concerned, we've got most of the world covered.
But the integration of the parts, so the CPU has to talk to your FPGA in some way.
Yeah, that's our problem. So that's what we do for a living. Yeah, that's what we do for the rest of my life. Is so. Any other? All right, so let's try to. I'm going to try to. So I think the best way to try to describe at least the flavor of the programming language in a very short talk is just by walking through an example. So I'm just going to walk through a simple example, which is an NBody simulation. I'll show a demo later. So we'll just consider one iteration of an NBody simulation. The idea is here we have a bunch of particles. Perhaps you're familiar with these kind of computations. These particles might be, think of, say, stars in a galaxy, or maybe they're molecules in a fluid. And they interact by some force, gravity, or some other physical force. And we basically have an n-squared calculation where in each time step, each particle will exert force on every other particle according to a physical law. And so there's basically 3 steps in the calculation. You generate the positions of the particles. You compute the force on each particle. And this is the expensive part of the calculation. This is the naive algorithms are n-squared, so each particle affects every other particle. And then there's a force accumulator. Once you've computed all the forces, you sum them up, and then you'll move the particles to their new position and then repeat. So if we wanted to do the accelerator model, it certainly makes sense very at a high level, since the force computation is the n-squared computation, the rest of them are linear. We'll start off by saying we want to accelerate the force calculation, and that's what I'll walk you through. So you start, as I said, you would start, so we'll imagine that we already had Java code to do this, and started with something that looks like Java code, the NBody class. The first thing we do is we need to tell the compiler, all right, we're going to have a task parallel structure. So we need to tell the line compiler, okay, we've got 3 tasks here. This is the structure of our computation, and these are the boundaries at which we're going to want to move code around. So the way we do that in Lime is we apply a task operator, which is a new keyword, to a method declaration of a Java method. So the code highlighted in green here is saying what we're doing is we're setting up 3 tasks. We're going to turn the particle generator method into a task, the force computation method into a task, and the force accumulator method into a task. And these are just regular Java methods. Ignore some of the strange array stuff for now. And then we have the connect operator, which is the equals greater than sign. This virtualizes communication. So this is saying that the output of the first task, the particle generator, will be fed as the input to the second task, force computation. The output of that task will be fed into the third task, which is the force accumulator. Now, so what we have here is very much a task parallel, coarse-grained data flow programming model, and that's at least the outer level of parallelism by which you'll express your computation. So for the rest of the talk, I think, at least on this example, I'm going to focus a bit on the GPU model of doing the data parallel force computation. But one thing I want to point out at this point is this task parallel model is very much in the spirit of hardware design, where you lay out data flow graphs of blocks, and there are constructs in the language to do splits and joins and matching and rate matching and so forth. So very often for hardware, what you'll do is you'll set up a fairly rich task graph, which maps down to hardware, and this is the kind of thing that runs well in hardware, because basically each task, if it's in a pipeline like this, corresponds to a pipeline cycle and a pipeline design. And so it's very much in the style of how people do hardware design. I hope that's clear. I'll go through a few more slides and then clarify anything that needs to be clarified. So once you've identified the task graph, which is what we've done here, the programmer will tell the compiler that I want to relocate a particular task, and we do that with these relocation brackets. And that's basically telling the compiler that in this case I want this force computation task to be accelerated, and then depending on how I've configured the compiler toolchain, it'll decide which backend it's going to try to. So let's assume for the moment, for this thing, that I've configured my toolchain so that accelerated tasks, the compiler is just going to assume try to send the accelerated task to the GPU. Now what happens is once you start to use these ensure brackets, some of these stricter type checking rules come into play. So at this point, the compiler will start to check that this force computation task, not only that it's legal Lime, but that it actually obeys the constraints that it needs to know in order to ship it off to the GPU. So in particular, the properties I mentioned before about isolation and parallelism. And so in particular, you'll have to start telling the compiler information about the force computation task. So I'll get into a little of that over the next few slides, but just to show you the method declaration in particular, I've said local. This is going to basically enforce that this force computation is isolated. So we don't have a general shared memory model. Each task runs in an isolated address space, so they can't read and write random access memory across it. The only sharing of state between tasks is through the inputs and outputs. And so the local qualifier guarantees, tells the compiler to check that that property holds. We also have these immutability constructs, which I'll describe a bit on the next slide, I believe. Yeah, so let's look at the code a little bit more. So what do we need to do in order to get this computation running on a GPU? So I mentioned the local. The local says this is an isolated task. What that means is basically the compiler at this point is going to check that the inputs and outputs to this task are values, that is, they're immutable, so that they can't be written or read or observed changing by other parts of the system while it's in transit. We're going to enforce immutability, which basically tells us this value property for the inputs and outputs. So that funny array syntax we have on the inputs and outputs of force computation, basically this is saying that the input to the force computation method, which we're turning into a task, is an array of 4 tuples of floats, so it's a 2-dimensional array, but it's immutable, so nobody else is going to be scribbling into it while this task is running, and it's going to return an array of 3 tuples, which is the forces, which is also immutable. The local keyword also tells the compiler to check that this calculation is transitively isolated, so in particular it can't read or write any global mutable state. So with that information, the compiler knows that it's safe to relocate this task and that it won't change the semantics of the program in any way. Now we also have, in this case, using the map operator, the @ sign. So what we're going to do is, this is a data parallel application of a function. It's the same as map, if you're familiar with map and list or any other functional languages, which is basically saying take this function, in this case the force function, and apply it to each particle, to each element of, in this case, an array. So basically this tells the compiler that we have a data parallel computation, and by, once again, using the same sort of annotations, local and immutability, we guarantee that there are no, in effect, loop carry dependencies. We guarantee that this actually is a data parallel computation and that we can effectively, if we were running on a CPU, we could execute these in any order, and that means that we can use the GPU hardware, we can fire it off in parallel, and we don't have to worry about sharing or the semantics. So this is basically the type checking here tells the compiler, okay, this is safe to parallelize and it won't change semantics. Now, if you violated these type checking, you'll get feedback during the IDE saying this method needs to be local, or this parameter is not a value, or so forth. And so the process of going from vanilla Java code to something like this that can be accelerated is effectively a dialogue with the compiler, where the compiler starts to give you warnings and then you can go in and fix them. And it's really not usually, if your algorithm is parallel, we think it's not too burdensome to do that. So I mentioned the map operator. This is a way of describing data parallel operations. We have, fairly rich. Well, the syntax is really pretty simple, but it allows us to express a bunch of patterns of data parallel operations. So we can map an operator. So when we say that C equals A at plus B, this is mapping the plus operator over each of the arrays A plus B. And this does what you expect, as illustrated here, is that we'll do an element-wise addition of the arrays A and B, producing an array C. There are many other patterns you can use to do data parallel. So you can apply methods in parallel. So this float C equals map the add function A and B is exactly the same as mapping the operator. And then you can also do lifting or promotion or currying, which is, for example, you can add 1 to each element of array, and by using this pound sign, it's basically saying lift this scalar value into array as an argument to the map function. So that's the basics of data parallel computation. I hope that was clear. Any questions before I go on? Right. So what we have here, I showed you the code for the NBody calculation. If you had programmed with OpenCL or CUDA, you know that this is much higher level and much more abstract than the current state of the art of programming using, in this case, OpenCL, where you have to do a lot of system level queue setup and compiling and management and manual communication. We're programming at a much higher level of abstraction for the GPU. If we're programming for the FPGA, if we're somewhat higher level of abstraction for GPUs, we're in several orders of magnitude much higher level of abstraction than you would write for an FPGA. If you're programming in HDL or Verilog, even very, very simple user logic, which you would express in Java, expands to very complicated state machines with low-level driving wires and concurrency and checking signals and timing constraints in Verilog. It's really a very low-level program model just to express the user logic. And expressing the user logic in a heterogeneous system is not really the hard part. The hard part is managing the communication between the FPGA and the host computer. It's not like you take an FPGA and plug it into your USB and the operating system recognizes the device and you start using it transparently. This is really a raw hunk of silicon. It doesn't come with an operating system, doesn't come with anything. So you have to write or find or acquire the IP to implement the device, implement the drivers on the hardware, and to have some sort of runtime system on the hardware to do all the routing between that. And so it's really a tremendous amount of work just to build the basic communication infrastructure between a device and a CPU. And so the gentleman asked the question, this is the kind of thing that we have done, and we've done it once, and we can do it once, and then our compiler can reuse it. So we have built the runtime system which manages the communication. Our compiler knows how to use it. So basically the programmer doesn't have to worry about it and doesn't have to know it. And this is, we think, a tremendous value compared to the alternative of doing this from scratch. Yes?
So you say you have a runtime system on the FPGA. So basically you have a small virtual machine kind of thing. You run it on the FPGA. You're running your programs or you're compiling directly into the FPGA.
So we're compiling Verilog. We're compiling directly down to hardware. And then our hardware, our circuits, basically, our runtime system is, calling it a virtual machine is perhaps a little too glorious. It's a bunch of queues with control signals and arbitration logic, basically to route data from the pins to user logic. So you would take our user logic, which basically exposes the number of wires, and then this is what our compiler does. I mean, the programmer never sees this. The programmer just writes local int foobar. What happens is the compiler, generates Verilog, which exposes a bunch of wires. Our toolchain hooks up those wires to the wires of our internal queues, and then our queues talk a protocol over, say, PCIe to our host, where we have drivers that know how to talk the same protocol.
So you could say instead of having a layer underneath, you have a layer on the side that actually managing communication in and out.
Yeah, that's right. I mean, it's really a bus and control logic. Any other questions? So we think, compared to the alternatives of programming FPGAs, we think we have a very compelling story as far as productivity. We're saving a tremendous amount of work just in writing the code. But a lot of the story here is not just about the code. It's really the toolchain as well, which, especially for FPGAs, but even for GPUs, where the tools and the toolchain and the process by where you use these devices, right now, the state of the art is very primitive compared to what we're used to with software. It's almost like going back in time before the invention of Fortran, and try to show you, what some of our tools do and what the alternative would be with the current practice. So, for example, compiling the code. In our system, basically compiling the code, we have Eclipse windows and launchers. So you would open up in our IDE, you would open up a specialized compiler wizard, which would walk you through how to configure your compiling for the FPGA, and then you hit compile. The alternative, using the tool chain that, as people do right now, is really relatively painful. You have to use multiple tools. It's all vendor specific. You have to write a lot of logic and test bench just to drive your logic to test it, work with simulators and so forth. And it's a very long, tedious process that takes a lot of expertise. And this is part of the reason, this is a large part of the reason of why it's very hard to get started using FPGAs. It takes a lot of expertise just to learn a particular vendor's toolchain. And then if you learn the Xilinx toolchain, that's not necessarily going to help you with learning the Altera toolchain, or if Intel's going to come out with something. So it's all, completely different from what we're used to in software, where it's almost like going back in time to the days before programming languages. So once again, as far as productivity, I think, we're making it much, much easier. Things that would take at least days, if not more, to learn how to do and to configure and get working, we hide behind a wizard and the system drives automatically. Debugging is a similar story. In our system, if our system is implemented correctly, the semantics of the program do not change whether you run it on the bytecode backend or whether you run it on an accelerator. The program should produce the exact same answers as long as our system is correct, which we hope it is. So you can debug your user logic simply by debugging it as if you were debugging Java code. So we have a Eclipse debugger integrated into Eclipse where you can set breakpoints and introspect and do all the nice things as if you were debugging Java code. What people do with hardware design today basically is they look at waveforms. And this is the level of debugging, which is the alternative today. So, we're at a much higher level than that. Now, our tooling will allow you to run on a simulator very easy and produce waveforms. So if you want to, for example, look at performance or look at what's going on, you can get to this low-level information. But for the vast majority of programmers we anticipate, they would never have to know that, that there are things such as clocks and signals and times, and they could do the debugging at a much higher level of abstraction. Once again, the whole theme here is trying to bring current practice in this world much closer to what a mainstream audience would be comfortable with. Running code is much the similar story, hitting a run button in the IDE as opposed to learning yet another tool, which is what you have to do to load bit files onto an FPGA and execute them and so forth. So there's just a tremendous gap in the experience of using a modern toolchain versus what the current state of the art is and using these devices today. Synthesis. So in order to compile a Verilog file or a VHDL file down to a circuit, you run a synthesis tool. This is a vendor-supplied tool, which basically lays out the logic, does the design, and tries to satisfy clock constraints and layout constraints and floor planning and come up with a design. So this is learning yet another tool. This takes a very long time. To run synthesis on even smallest user logic modules takes many minutes. Running for big designs can take hours. Often you'll run a synthesis and it will just fail because the tool wasn't able to satisfy some timing constraints or some clock constraints. So this is yet another area where we can try to raise the level and the experience. We've decided to do this by a cloud service we call LimeForge. So now for regular development, you can develop simply on your desktop. You can run in a simulator on your desktop and do all your development. When you're actually ready to deploy onto a physical device, you need to run the synthesis tool. You need to generate the physical bit file to load onto the device. And now you have to do synthesis. What we do is, to make this less painful, we've implemented a cloud service, which basically you submit your job where you ship your logic and the program over to the cloud. And our cloud will now run whatever it takes to try to synthesize this. So basically, it will, in the background, the cloud will spawn out a bunch of different synthesis jobs and search for different clock frequencies, try to maximize your clock frequency. There are lots of ways of tuning constraints to the synthesis tool. So our cloud will search through different constraints and apply expertise, which the experts on our team have learned over the years on how to drive these tools. So basically, we try to have a somewhat intelligence, maybe not the right word, but a pretty advanced system in the background using a lot of resources to try to get the best results from the synthesis tool. And once again, take the burden of learning how to drive this tool correctly and how to optimize this tool away from the programmer and try to do it automatically. And we do this in the cloud because this is very resource intensive. And so that's why we farm it off. As well as licensing issues, it's easier to just install one copy of the vendor tools. So that's it. I've tried to give you a flavor of what we're going for, at least for developer experience and what the system's like. I could talk a little bit about the implementation. Any questions at this point before I go on?
Just about. You said you also took the pain out instead of going IC because you just took it to your account, or?
Right. Yes. we have a sale. Yes.
With these tools, the skill of the people who do FPGAs nowadays with these tools, will that go away, you think, or will it still be relevant?
Well,
Will it be a bit like assembly programming, or?
You could think of it. I'd like to say yes, we'll put them all out of business. You know, and I think for the vast majority, if we're successful, we will. There'll always be, I think, reasons why you want to go down to low-level design for some parts of your code or for some applications. As far as our system is concerned, there's a few reasons why you might want to. So we've got a very high-level programming language. We've made it very easy and safe to express parallelism, but we've taken away some of the power to express arbitrary forms of parallelism from the programmer. So you can't express arbitrary concurrent structures in our language. So if you want to write an arbitrary design with queues which are communicating on a clock-by-clock level and be very careful, you can't express in our language. So for that, you'll have to drop down to a lower level. And that's, for example, how we implement our own runtime system. We don't, our own crossbar queues, we don't dog food it, we drop down. The other thing is just the question of what's the maturity of the compiler. Right now, there's a tremendous gap between our source language and what we're compiling to, and the compiler is still relatively immature compared to compiling to assembly language on a CPU, where even that took basically 30 years of development. You know, we're solving a much harder problem, and our compiler is just not that mature yet. So you're definitely going to give up something, probably, if you use our compiler, either performance in terms of clock cycle or throughput, or area, more likely. Our designs may not be quite so space efficient. One thing we do have in our system is what we call LNI, native interface. So we do export interfaces whereby you can write your own logic and link it in to our system. So one possible use model is if there's write everything, and if there are less performance critical parts of your design, perhaps logging or some control structure or some debugging code or RAS code, you might want to write that in our system. But for something which is really super performance critical, you would write that by hand and then link it into our system, just like you would do perhaps native code into Java today. We can also go the other way. We can simply export Verilog from our toolchain, and you can take that Verilog and do with it what you want. So you can use our compiler basically as like a C to gates, just as a higher level Verilog design thing, and then you can plug it into your own infrastructure and worry about. So it can go either way. It depends on how much pain and how much performance you want. So let me talk. Oh yeah, I should get to a demo, shouldn't I? Well, I don't know. I might regret saying that. So as I said, the implementation is something we call a Lime virtual machine. The Lime virtual machine basically is our abstraction of a virtual machine of an operating system, and parts of it will run on the CPU and parts of it will run on each device. And basically the job of the virtual machine is to take code, load it, run it, and manage the communication between different tasks. And so this is basically our whole runtime system. This is a lot of the effort we've put in. I think I'll switch to a demo at this point. So actually that NBody calculation, which I described, has actually been running while I've been giving the talk. So here, I'm running the NBody calculation. I'm actually right now running it on the JVM. And I guess the key number to look at right now is I'm getting about a gigaflop a second. And if you look at you probably can barely discern the motion of the particles. It's going pretty slow. So I can tell the runtime system migrate the force calculation, which in my code was this compute forces method. This is a panel exported by our runtime system, and if we tell the runtime system migrate it to GPU, so what our system just did was take all the state of that running task, ship it over to the GPU, connect all the queues and data motions so that the data is now going over to the GPU and back for the force calculation task. And now we're running on the GPU. I'm getting, I guess, about 5 gigaflops now. Hopefully you can at least see the data moving. Of course, it would be much better on a machine with a much better GPU, but the point I wanted to show you is that the runtime system is very dynamic. It can move tasks around because we have isolation. Things can move, and everything just gets managed transparently. This is all the same code, which happens to be running depending on where you want to run it. If I had an FPGA attached to the system, I could move it there as well. So I just wanted to show you a demo that it's that easy to test moving things around and to write code which works across different systems. So in particular, when we're using the GPU, such as the demo I just showed you, the real structure of the virtual machine looks like this. We've got part of when I was running on the GPU just now, part of the code was running in Java bytecode. We have a C glue layer, which both talks JNI to the JVM to get data from there, also manages the GPU device using the OpenCL API, so data will get shipped from the JVM to this C wrapper layer, which is then managing the OpenCL kernel on the device and handling all the low-level protocols and things used in OpenCL. So that's what it looks like for the GPU. You could imagine similar structures, although it takes a lot more work for the FPGA. I won't get too much into details of performance. I guess I'll just try to say the bottom line of performance. So, I think we have a very good story as far as productivity. I think we make a pretty convincing claim that you can be much more productive at doing this kind of programming using our system. The question is, how much are you going to, what are the performance consequences of doing that? Because using these devices in the end is all about performance or power performance. So there are two ways to ask this. To answer this question, one is to say, if you're a Java programmer and you start to use the system, how much faster than your original Java are you going to get? That is, how effective can you be in using these accelerators? Or perhaps if you're an expert, the question you want to know is, how much slower is my program going to be if I use this system than if I had done it all by hand by an expert? So we have to evaluate both. I have numbers. I probably won't go into them in too details. The current status, we're not trying to build a magical supercompiler. Our compiler is fairly sophisticated. I think our group at IBM is very strong in compilers and will do about as well as we can. But on some benchmarks, Lime performs just as well as a hand-coded alternative, and some not. We have to worry a lot about communication-computation ratio in particular. So this is what we're working on all the time. I think our performance story on the GPU right now is pretty good. I won't go into these in too much detail, but there was a paper we published this year at PLDI, Programming Language Design and Implementation Conference. And for a suite of GPU benchmarks, we're able to get the dramatic speed ups that other people have reported on using a GPU, using our Lime program for a variety of benchmarks. And at least for OpenCL for the GPU, on these benchmarks, we're within a ballpark of what you could expect of what hand-tuned code would do. So we think for the GPU, for a pretty large number of codes, we have a pretty good performance story. The FPGA, we're still working on the performance story. I don't have any numbers to show. For basic combinatorial circuits, basically things which don't involve loops or state, I think our performance, although maybe not necessarily our area, is as well as you can get in this effect that we can get single cycle pipelining of the circuits, so we can, for any tree of combinatorial logic, our compiler will produce a pipeline design that can produce one output per cycle, which is as good as you can get. We might not get this, we might use more space, but we're getting closer. For complex circuits right now, the compiler is worse about a factor of 10, so we're doing a lot of work on I/O pipelining, and we're pretty hopeful that we're going to be able to get this down to within the ballpark, within a factor of 2 or 4 of what a hand-tuned, of what an expert programmer could do within within the foreseeable future. So, and then you'll have to decide whether or not that the productivity versus performance trade-off is worth it for you right now. And I think these numbers will just get better over time as our compilers mature. We also are working on, there's a lot of issues which I won't go into here as far as supporting high-level languages features such as dynamic memory allocation or virtual method or object-oriented dispatch or things like that. And we're working on ways to support these language features on the devices. We had one paper recently describing how we're going to do garbage collection on the FPGA, which is an excellent paper. That also was in the PLDI conference, so that's definitely worth checking out if you're into this kind of design thing. So Martin asked, what's the summary? As I said, I think we have a pretty good story on productivity. We've shown that we can have high-level concise abstractions for parallelism that map to different devices. We've shown, I believe, or at least our experience, is that the experience of using this is not much harder than Java, and so orders of magnitude better than the current alternatives. And I think we have a good chance of delivering on our goal, which was the general solution for mainstream programming of these systems. Now, of course, as I said, there's no magic. We're not going to design a parallel algorithm for you. This is not a parallelizing compiler. You still have to be able to design your algorithm in a way that's amenable to parallelism. We're not going to pretend that one version of the program runs well on all devices. You might have to write different versions of a method in order to satisfy the constraints of different devices. We're not trying to run vanilla Java programs on an accelerator. You do have to go through a migration step dialogue with the compiler. This is an internal research project right now, so this is not yet available to the public. I'm not prepared right now to make any announcements of this. I'm hopeful that this will be available in one form or the other relatively soon, but for the moment, this is an internal research project. We're piloting it with various groups within IBM to get experience and harden the system, and we're hopeful that this experience will validate our hypothesis that this is a productive way to go. So I'm done, and I'll stop here and answer any other questions you have.
Is there any way to participate from outside? Not yet.
If you're an IBM customer, talk to us. We might be willing to do some sort of one-off, first-of-a-kind agreement if it made sense. So we are doing this, or we're in discussions of this with several customers. There's no reason why we couldn't do more. So we're happy to engage. As I said, though, it's not open public, so it has to be done under the appropriate legal agreements. Yes?
The interface system, that's PCI expressed at the moment. Is that the only possibility of one?
Right, so for right now, both the GPUs, so let's see, for the GPUs right now, they plug into PCI things. Now both Intel and AMD have integrated GPUs on the same core.
I was thinking of FPGAs.
So the FPGAs, there's a number of ways to communicate. Right now, yes, our main system is communicating over PCIe. There's also Ethernet is a possibility. We also have, for prototyping, we have a UART serial connection. So there's many different ways to talk to FPGAs. There are also vendors that do memory bus attached FPGA designs, either with IBM or with Intel. So there's a number of ways, but yes, our primary platform right now is PCIe.
Other than the demo that you showed, are there any interesting stories of applications that have been tried? You showed the benchmarks also, so we have a set of benchmarks and your demo. Any other interesting stories?
Interesting stories. Well, one thing we have fun with internally is that it seems that most of our compelling applications are evil. So we have a lot of stories from, applications from high-speed high-frequency trading from Wall Street and weapons and, so I guess that's the story with all sorts of high-performance, bleeding-edge technology. The early adopters tend to be people with a lot of money and power. I try to concentrate on the non-evil applications, but.
Do you see it as an alternative to classic? Right now, you can see from offloading a load to the FPGA board perspective. Do you think it would be possible to use this high level for doing some pure FPGA projects in this line language without the attached PG?
Yeah, so I think of the scenarios I started at the beginning of the talk with, my personal opinion is the one that's most attractive is this, is network attached. And in this case, basically, in the common case, all the computation will be done in the FPGA. And I guess in theory, you could cut the cord and just detach the FPGA, but in practice, it's usually attached to a host because you have to boot the device and load things like that. But yes, in most of these applications, the idea is, and we've been doing some of these applications, especially encryption. Encryption's an interesting one. Zipping, gzip. Gzip's a very interesting application. But the idea here is that we're doing some filtering directly on the wire, at the speed of the wire, ignoring the whole software stack on the CPU for very low latency, high throughput. Now, gzip is an interesting application. There are I don't know if you're familiar with the algorithms, but there are static and dynamic versions of the Huffman algorithm. And people are doing FPGA compression apps, but they're compression algorithms, generally speaking, that you do in software, which use dynamic Huffman schemes, are more effective with compression, but they're extremely difficult to map to hardware because they use dynamic structures. Yet, this is the kind of code that in theory, well, actually in practice, that we can express in our language, and if our compiler is able to code it, is able to implement it well, we can actually use a better algorithm. So I think this is an example of the possibilities of where using higher level abstractions, perhaps counterintuitively, you can perhaps get better performance by using a better algorithm, even if the operation by operation code generation for very low level stuff is not as good as doing it by hand, the ability to use a smarter algorithm at a high level may actually be more productive as far as the bottom line story. So that's one application which we're pretty happy with going on in the FPGA, and there are a number of others.